Hello and welcome to WinCC Open Architecture. This is your host Markus, and today we are going to learn more about the platform, what make it happen on the IIoT platform for engineers. And I'm really glad that we have taken so many of you into this conference that we can spark the interest of our platform. And why many of you are here was the reason because we did a seminar, we attended the ProveIt conference in Las Vegas, and that I want to share with you that we were having the information from Walker Reynolds, the mastermind and event organizer of this, and had a nice statement for us in the preface of this conference. And that is what I'm going to read for you first. If there is a vendor who is going to surprise you the most, it's going to be Siemens. And here is why. Most people think of WinCC OA as an HMI platform, but it is not. It is a rapid application development environment, a platform for solving problems. It's an IIoT platform. And that actually describes WinCC OA very well. And that is what I also want to share with you, because not all of you have been on the ProveIt conference. I want to share with you first what the solution there was, what we did present, and therefore also what may have sparked your interest in WinCC OA. So the ProveIt was an industry-focused conference where the different vendors who were invited have been invited to present their approach on solving a real-world challenge. What was the real-world challenge? It was to get the data from a virtual factory with the UNS, the Unified Namespace, as the central information layer, collecting all the data from different machines, then doing something with this data, and then demonstrating whatever value of their offerings they have in front of a live audience. And that, of course, was quite a challenge because real-life problems are, of course, the most interesting to solve. What was our approach there? The approach was the following. The data was acquired by the field equipment via UNS. The MQTT broker was the source of information, global and for the whole factory. The data was provided with MQTT to this broker and to the central data layer. And of course, also Industrial Edge was there of doing some additional enrichment of the data on machine level, where, for example, Performance Insight or Machine Monitor was used as an app to have some KPIs and other things calculated. And then, of course, on the process orchestration layer, we have WinCC Open Architecture linking to the UNS, importing all of the structure automatically. And this was done by our solution, what we have provided with our really flexible IIoT platform that is, first of all, ready to run in every environment. That means on Windows, on Linux, and also virtual environments. Also, it runs on any hardware, what you can think of, starting from the smallest, like, for example, the Industrial IoT 2050 or even a Raspberry Pi, then ranging up to the bigger machines. But we will come to that a little bit later. It is also fit for doing OEM customization and will have a full set of security certification and even is certified to be used in a safety environment. By the nature of WinCC OA and its event-based communication, it also features that we have an online engineering, what I will demonstrate later on. And what we did then to solve this task, to synchronize with an existing UNS, is with our additional scripting language, what we introduced in the latest version, Node.js. We have used a solution with JavaScript where we interfaced with the UNS directly to browse the existing structure from the broker directly, create all of this data necessary in our system without the need of any manual engineering at all. and they create internally the data structure, all the necessary data points, all the configuration to get, and also then, of course, send other data, what we then have done for calculations out to this UNS data broker with MQTT, pub, and sub. Of course, this can also happen with OPC UA, and that is, of course, the flexibility then also what you have. Additionally, we did show that we also had a notification app provided. This was another Node.js application, what we have done in the forefront, and it was able to get alarms, acknowledge alarms with the Telegram, different Telegram channels, what you have in this app solution, and view also live trends if you want to request something from the plant, and also giving commands if that is necessary. This application, by the way, is also for download on our Git repository if you want to check out at a later time. All of that was happening because of the capability that we can do engineering during runtime without any downtime, and also without recompiling or anything else. This was just done with some scripting in the background. Everything was created live, and that I will also show then at the end as a little demo with another application. The visualization, of course, can also be adjusted during runtime. Our dashboard, fully HTML5 capable. Of course, the operators can prepare their own dashboards on the fly, save them, modify them to their needs, and will then have a nice solution what they use every day. Additionally, of course, what is for sure the thing what you want to do with all the data you gather from the field is you want to take some benefit from this data, and that we're using our Smart SCADA add-on for. The Smart SCADA add-on enables you to calculate KPIs. There's a toolbox available to do analytics, and for the analytic part, you can find maybe things to optimize in your data within your KPIs, and also, of course, it will provide you with some decision-making capabilities, and of course, also very important, predictive maintenance. At an enterprise level, then we, of course, would need to communicate to ERP systems or MES systems to exchange data. Between this, we use the REST interface. There is also the industrial copilot for operations from Siemens available, so that we can have an also an AI-enhanced experience in our daily situations. Well, that's it for the ProveIt showcase that you have seen in detail. Many of you have seen in detail. For the others, it was just a short recap of what we have presented already. Now, let's go ahead and check out why this all was possible with WinCC OA. And let's first have a look at what is the usual IIoT data integration use case in your every life situation. There will be, of course, standard interfaces where we collect the data from the field, and in a greenfield situation, you might be lucky and in your factory you have only OPC UA and everything is nice and fine, but of course, there will also be other field protocols supported. We support more than 20. I will show you later which ones they are. And in a brownfield situation, but you will have many others as well. There will be Modbus, Ethernet IP, and others. And all of them, of course, you want to collect and use in your data model. But then, of course, you want to decide what is the data model, what you use internally. We, of course, can pick freely what is the data structure, what you use in your application, and you're just wiring it to your different applications, to your different equipment under control from the different PLCs, from the different vendors, in a way that no matter how it is called in the different machine, of course it is then showing up on the very same structure in your internal data integration layer. And that is also why it is called data integration layer, because you can freely pick how you structure the data internally, and then of course also what you do additionally with the data, because that is then what you need to do in the system. You want to enrich the data with additional information. You have business logic there to calculate some additional stuff, KPIs. Maybe you want to have different value ranges, what you use. Then, of course, you want to use this data not only now, but later. That means also a reliable historian solution is necessary. Of course, we will also demonstrate how this is done in WinCC OA. And then, of course, you are going to, after all these calculations and whatever additional things you have done, you're going to serve this data to other IT consumers. And that is, of course, the ERP systems, MES, or you want to send some data to the cloud. Maybe there is a database in the cloud. Maybe there is the Insight Hub from Siemens. Maybe there are other stuff. And that is then happening with either direct interfaces to databases or with some scripting, with web server, with REST interfaces, and all of these kind of things. So, but that is the idea of how to connect the widespread different protocols from the field to a central data integration layer, and then, of course, serving this data maybe to UNS with MQTT or these kind of things. Sure, all of this must be secure because very often our system is used in critical infrastructure projects, and cybersecurity is of the essence, of course. So that is also a thing what we can prove. And when you now think about all of these things, what we need to do in an IIoT integration use case, and we can think about what are the biggest challenges to be solved actually when we have such a project at hand. And for this demonstration today, I've picked these four big challenges. We have the connectivity challenge. How can we get the data from the field? How can we present it northbound then to the IT systems? The data integration, what we do with the data, and of course how we scale that internally and so on. The scalability, because you don't want to start with a system that can barely do what you need to, and then when you extend your plant, you find out, oh, I would have need to take another solution or whatsoever. But we got you covered here. Trust me, we will see in a minute when we check out how scalable WinCC OA is. And then, of course, security is of the essence. We mentioned it. So also here I go to convey to you what are the security measures which we have in place, what you can expect from a system like WinCC OA. So let's have a look at our first challenge, connectivity. Now I mentioned that there are a lot of drivers available in WinCC OA to collect the data from the different PLCs, telecontrol systems, and other devices, what you might find. Let's quickly go through it. There is, of course, the need to connect to normal PLCs like SIMATIC PLCs, for example. The whole wide range of SIMATIC PLCs can be used by our drivers, what we provide, a 7 or a 7 Plus driver for the newer PLC. Modbus is a very popular protocol for other vendors' PLCs. And also, of course, other devices. Ethernet IP for the Allen Bradley PLCs and all of these kind of things. Xia is a Swiss product. ProveIt, and of course also ProveSafe, because I mentioned we are safety certified as well. And then, of course, ProveSafe is, of course, some driver protocol what you would maybe plan to use in this case. For the telecontrol systems, we have the IC 6870, and of course we have the 101 and the 104, so that is the serial, and this is also the TCP connection. Sure, for normal, the TCP connection is used here. And the IC 61850 comes also, of course, with the 61400, what is for the wind, but the 61850 comes with a complete set of engineering, and that is for the energy market, as many of you might know. The TMP3, more often used in the water projects, and CNOUT, of course, is the IEC take from Siemens that is also supported in WinCC OA. MQTT as a base for connecting things from an existing broker, of course, is one thing what we have. We will also find this then at northbound interfaces for publishing data, of course. So that is primarily now the southbound interfaces to read data from these different field protocols. BACnet is the building automation standard, and we support the advanced workstation standard, of course, officially certified by the BACnet Foundation. Then OPC, that's the industry standard anyway, and of course the new one, OPC Unified, the UA is of course available for data access, alarms and conditions, and also the historical access, sure, but we support the same for the old OPC standard, OPC, DA, A&E, and HDA client, that is also supported in WinCC OA. And by the way, all of that drivers, what we see here, of course, are available on Windows and Linux. It's just that the OPC, because it relies on DCOM and COM, is only supported for Windows. But as a general fact, everything in WinCC OA will run on Linux as well. In some cases, you want to, of course, in many of the cases, you want to monitor your network devices. So routers, switches, hosts, and other things you are going to monitor with SNMP, of course. And database interconnections, of course, you can do for historical data, but also you can have manual connection to databases, third-party databases, and do some queries and interactions with it by our ADO ODBC interface. File transfer is also possible. As a last thing what I want to mention. And the very last thing is when there is no driver on the list, what you fancy, and you need something very exotic, there are some things what we have on request. So don't hesitate to ask if there is some other driver available, like for example, 6gem for the wafer manufacturing and those kind of things. So there are some additional available. And if not, you find it on the list, then you do your own if you want with our API interface. The API programmable interface is the C++ environment where you can create your own drivers if you need to. The northbound interfaces, what we use to connect to the IT systems like MES systems, for example, and so on. We also have many of those. Here we start with the HTTP server, our web server. We can, of course, give data to external sources on request. There is a REST, not only one REST interface, there are multiple REST interfaces available with what you can exchange data. You can request data, not only live, but also historical data with it. Can use it for reporting purpose, like with Power BI and those kind of things. You can also have the communication to Ops Center execution core. This is an MES system from Siemens, right? And also there is a REST interface for the PM add-on tools, also from Siemens. For giving data via OPC, the old OPC, but also the new, the OPC UA, we have all type of servers in our system as well, not just the clients, what you have seen on the first page. There is the DA, data access, alarms and conditions, historical access server, what we provide for both OPC UA and OPC technology. Modbus server is also available in the rare cases where you might want to use this, but literally speaking, OPC UA is the go-to standard. And then, of course, MQTT publisher. Sure, the MQTT publisher is also used for exchanging the data to, for example, the UNS, Unified Namespace. But there is also an Insight Hub connector. Also, Insight Hub from Siemens is supported right from the application to help you connect to that additional piece of technology. Database connections also, of course, for sharing the data to the other databases. And sure, you can also do here your generic drivers if needed. Very often, then managers can be created which open a TCP port to a certain other application, and you would exchange data with this custom done manager. And then you're using the C# or C++ programming for that. Then we now take a look at data integration, because now we clarified how we can get to the data And then, of course, we now clarify how can we keep the data internally and to keep it in a way how we can select the structure of our data. In WinCC OA, you have an object-oriented data model. The object-oriented data model means that you have a type instance, what you create first, and that is a tree-like structure. So you do a model of a real device. So your everyday devices, what you have, valves, motors, drives, whatever, pumps, something, that will then be a data type in your system where you specify, okay, what signals do I get, which commands do I send, and the best part then, of course, when you did the type one time and you do many, many instances of this type, when you do any change later, because it's a type instance concept, of course, the change will be valid for all the instances immediately. Sure, then is also some mask configuration to be done, but that is then the additional configuration what you do to wire it then to the different PLCs and field devices and so on. But that's the point. We select how we store the data in WinCC OA completely freely. So either flat model or structured model like this. And then other thing is how we serve the data then to the northbound interfaces with MQTT to we present a completely different structure with the ESA 95 model or in any other way you want. Then, of course, we are going to have a long-term archiving in place. There is, of course, not only the long-term archiving, but there is also the configuration of the system, which needs to be stored in some database. And this database, what we use for storing the configuration, but also the process image, the persistency of the system, and not only the values, but also the alarms, all of these things. So persistency, configuration, data point type definition, all of that, this is done with a SQLite database. The advantage of the SQLite database is that it is 0 voltage safe. That means even when you kill your server unexpectedly, the database will not get damaged. And of course, it is year 2038 safe, and it will have no limitation in how many things you configure in your system. But we will see later a little bit more about that. Now, the historical data, we have a modular concept, the next generation archiver, and that is a front-end, back-end concept, what we do here. We have all common functionality built into a front-end that does things like buffer to disk, message splitting, and the query engine, and all of these kind of things, which are common in one manager. Yeah, and then, of course, we have the different database technologies which are free of choice. Yep. What we provide in the actual version of WinCC OA is Postgre as the go-to solution and primary idea of what you should use in a new project. Influx database as also a nice solution for storing the data in a time series manner. And then, of course, Microsoft SQL Server as the second relational database. There is also Oracle available as a solution, what comes a little bit with a higher price tag than the other solution, but for our biggest applications, Oracle is also rather popular. Now, when we now talk about keeping the data internally, the system itself is built with a micro modules concept. We call it also manager concept, because the different parts are splitted, of course, for the different modules, which all fulfill their specific functionality. And of course, we always start on the bottom. That means to collect here all of our information, it's job of the drivers. The drivers will then, of course, we have different field protocols, like what we mentioned in the first place. But then, of course, this information will be sent to, and that you can see here in this graph, to obviously one manager, what looks more important than all the others, because he is in the center of all things, and that is the so-called event manager. Why is this thing called event manager? And what he is used for? The event manager is center of all things. He is your single source of information and deals only, of course, with all these value changes that come in from the driver and then needs to be transferred to all the other subscribers, like user interface to display the information, or some of your business logic, control scripts, or other things that calculate some stuff, and then also the database and so on. So here's the single source of information and the distributor of all the information in the system. And why is it called Event Manager, by the way? Because WinCC OA is fully event-based. Event-based means when there is no change of data, you do nothing. The system does exactly nothing, has no load. There are a lot of systems out there which have a polling architecture, but that is not happening with WinCC OA. We are strictly working on the change of data. And this is also why we can have the millions of tags on one server. It is not really a problem how many you have on one machine. Why not? Because that's just a little bit of more RAM what you use, and WinCC also has a very low memory footprint. One tag will only be round about 1 kilobyte of additional RAM what you need. That means for 1 million of tags, you will use round about 1 gigabyte of RAM. That's it. And you have plenty for normal in a normal grade server. But that makes it also suitable for having the very small applications, the embedded applications. And we can also, of course, then have it on embedded hardware like a Raspberry Pi or things like this. Okay, Event Manager as the distributor of all things. But then what does it distribute? Only when there is a change of value, of course, and when a user interface, for example, is now displaying whatever part of information on the screen. This is the only thing what you subscribe for. That means the user interface and every other manager actually does not have a full process view of your million tags, what you have, but only what is needed at the moment. So the subscription is done on demand, and then this information is sent by the event manager to this other manager. And when there's a change of pictures and panels, then of course there is other information you subscribe for, but that's the idea. And then, of course, only the changes are transferred. So also we can cope with small bandwidth connection and also with, therefore, bad connection to user interface like you would face when you have a cell phone or things like this, tablet, smartphone with wireless connection and these kind of things. Then you also see that the database, this is the persistency, what I talked about. The event manager only takes care about main memory to be extra fast, of course, and to be able to have the 250,000 value changes per second worked on a normal grade machine with 50% CPU load. He's doing this with RAM and not interfering with the hard disk, of course. But the data manager, then on the other hand, is providing the configuration in the first place, and also is in charge of doing the persistency. So in the case there's a value change, the event, of course, also sends it here. And then when the system is restarted, of course, it will come up with the last recent known values. And then behind that, we will find the next generation archiver, what is then putting the data, what you have selected to be archived permanently, then into the archives, into the databases of your choice, like Postgre database, for example. Redundancy and distributed things I will explain on the next slides. But first, what is important, what I want to convey is some driver protocols already feature the unsolicited message communication, but some other does not. For example, OPC UA, you can subscribe, then you can tell the server, only give me the information when there is a change of data more than 0.5% or something like this. Also, the SIMATIC driver can do that and many more. But some cannot. For example, like Modbus, then you need to poll. But that is now the important thing, that when we have, and of course this can be done by any driver, this Modbus was just an example, Then we have a polling driver that is then recurringly getting the data, of course, in a very frequent interval if needed. It will not be a very high load to the system. Why not? Because we do immediately old-new comparison, low-level compare with an XOR very fast to get rid of the same data, what we get over and over again every 100 milliseconds when we do a very fast poll. And imagine a situation for alarms, for example, when you have an alarm and this is a Boolean signal, what is false the whole day long. You can poll it very fast. It is no load to the system at all, only a little bit in the driver, of course, and it gets rid of this repetitive same values immediately when he receives it, old-new comparison. The transformation is then transforming it into a value itself. On Boolean, maybe the old-new comparison is good enough, but for analog values, you can do additional calculations, but we do it in the driver, not to do to have the load in the rest of the system, but to have it prepared as deep down in the system as possible. And that might be already in the PLC, but if it's not in the PLC, you do calculations here. Conversions can be polynomial operations, linear operations of some sort. You can do rounding or things like this. And after that, and this is now the important thing, is the smoothing. For analog values, we need to have this last quality gate where typically you would do the value-based deadband, where you filter the noise. An analog signal comes with noise, and this is what we want to get rid of, and that's the place where we do. So the driver is doing a lot of pre-processing of the data, but we have maybe 1 million tags what we connect. And all of this incoming data, maybe one driver is not strong enough. Then, of course, you can have multiple. You can have 255 drivers connected to one event manager on one server. Every of them could run on a different core. That is also how we scale on the bigger servers, that we are utilizing all and each of the cores of a machine. Driver will use one. If you are in need of multiple, of course, you start even multiple drivers of the same protocol type. No problem at all. Then the event manager, of course, distributing the information, then the database, long-term archiving, maybe some business logic, what you do with the control managers. And I didn't mention, we have the multiple programming languages available here. Control is the internal scripting language. The API interface comes in C++ and C# for doing the additional managers and also additional drivers. And the Node.js is the new thing here, where we have the capability of doing JavaScript and TypeScript and integrate ready-made solutions maybe from the Node.js environment ecosystem. So that's the situation. That's the manager concept. This is why we utilize the bigger servers nicely. And now let's continue with scalability. When we now have the idea of what a system can do on one machine, the question is, on which machine? You can have the very same installation on the smallest possible hardware. And it is not only the IoT 2050 what would I deem to be the smallest available thing. It also installs nicely on a Raspberry Pi if you want to use that. Then, of course, a whole range of industrial PC solutions. This is now the product lineup from Siemens, but of course it runs on any hardware what you throw at it, literally speaking. From the smallest up to the largest, multi-core, no problem. That is how we scale for one system on one machine. And of course, all of that can run in the cloud. Now we have RISC-based architectures. We have the x86 architecture, what we do build for Linux, Windows. We support multiple Linux versions here. But also Azure and AWS is supported, so also the WinCC OA can directly be installed in the cloud. And what is an installation? It's around 1 to 2 gigabytes, so installed maybe a little bit more. Installation happens in like 5 minutes to any of this hardware, and you have a running system. But then maybe sometimes one server is not good enough. You have the bigger applications. You have multiple reasons why you want to use multiple server architectures. And now there are different architectures available. Let's have a look at the first, the scale for the scaling for performance reasons. When you have a big plant, you have millions of tags, and also with a lot of value changes per second, because million of tags you can do on one machine. And at CERN, by the way, they have machines where they have, for example, the control for the electrical environments there, what they did with only one system, but it doesn't change very often. They literally switch on the power, then run for a very long time, and that's it, actually speaking, and only monitoring alarms and so on. So when you only monitor alarms, you can have millions of tags, and this is not an exaggeration on one machine, as long as they don't change too often, because that is the limiting factor, value changes per second for a certain hardware type. And if you run in a limit, then you use 2 or 3 or 4 or many more. The limit is 2048. And systems like the New York Metro, where you have 500 servers distributed and then brought together to central control centers, then we talk about this other approach here, where you have multiple subsystems in different parts of the world, and that can be maybe in the same city, in different cities, everywhere in the world. And then bringing all of this information together to a so-called head system in the control center. The main control center will then have, of course, direct access to all of this data because of the unified naming layer what we have because of the data integration. All of the tags internally, all of the data points have a unique name because of the unique system name. They can also be, you can have the situation that you have a large number of very small systems. For example, machine 1, machine 2, machine 3, small IPC you put on the machine, and that comes already with central archiving and all of these kind of things. And you have then to collect the data from many small things out there in the plant and directly stream the information to some center system. And then you don't do the distributed system approach because of performance needs, but because you have many small things of the same stuff, what you want to nicely integrate into your bigger application. But as I said, it can be a hierarchical disk where the subsystem will not take the information or get the information from the other system. This is your decision what you have by adding one more line to the config file, that this subsystem can only communicate with the head, and that also, or in this case here, that every system sees the same data, because our connections, what we do, are logical point-to-point connections, and therefore you can build hierarchical networks, or you can build fully meshed networks as you see fit, yeah, for your application. Now, when we now speak about critical infrastructure and high availability, what we also have, what's very important to mention, is the hot standby redundancy. The hot standby redundancy in WinCC OA works in the following way. 2 servers are doing exactly the same at the same time. One server is the lead server, the active one, what is then synchronizing the other. And but that's the important thing, that's typically both of the servers would get the information, request the information from the PLCs, from your field at the same time. Only the passive one is discarding it. Why is this? To have data integrity, that we be sure that we use the very same data, what traveled only one path with all the calculations and everything in all of the cases. And when there is a switchover situation, because there is a partly failure of one of the 2 machines, the switchover is, of course, seamless for the user interfaces and for the other processes. Seamless means the switchover happens in some milliseconds. Of course, typically you do after the switchover some additional things like general query and so on, and there is then some work for the system to do afterwards, but the switch is really fast. Or one machine dies with blue screen, and therefore, of course, the other previously passive one has all of this communication already in place, and will of course have a little bit of buffer of the messages not yet discarded, but when the other is detected dead and then it gets active, then you have also a seamless flow of information in your system where nothing gets lost and ideally nothing gets done twice. So hot standby redundancy. But actually, this can be now combined to the even bigger architectural solution where you mitigate other risks. The highest possible risks that can happen to your plant might be a catastrophic event, a disaster to your main control center, where the main control center is wiped from the existence of the earth because of a tsunami, fire, flooding, earthquake, I do not know, terrorist attack, plane crash, you name it. Yeah, and then you would have a second control center in a completely different place. For example, 300 kilometers away in a different city. When you do things, solutions like the national power grid of a country, then you want to have such an approach where you have a complete, fully redundant control center, and you have a second one just in case. Because you don't want to waste, of course, a perfectly nice control center. In most of the applications, people are, of course, constantly working in both of the control centers. 20 people sitting here, 20 people sitting there, but only one of the two is active at the time. And why is this? Because typically your field devices would not support 4 parallel connections. Then, of course, the system does it like this, not only one, what is now in the role of the active system is gathering the information, in this example here, the primary server system. And of course, this is hot standby, and one can fail and the other will take over, no problem with this. But if both fail, yeah, if the complete thing is gone, yeah, then the other system will detect, and then the other driver will go live and then gather the information from the other side. But that is why that is now called only a warm standby system, because it takes like 2 seconds or what for the system to decide, okay, the other system is totally gone and no communication possible, and then we go live. So that will mitigate the highest possible risks for mission-critical operations. Of course, that can be combined then to the more complex applications and architectures where we have, no matter what is on the field, on the sub-level, where we have maybe redundant systems, maybe no redundant systems, but in this case it is 3 redundant WinCC OA server pairs, but it can be many. 2048 is the limit, just keep this number in mind. And then they will be connecting to the head system where you have the main control centers, and to the local control center you only go in case of emergency, and you would not do this typically. So they are not meant typically. But this is completely now free of choice, where you have some user interfaces, or you can start user interfaces. It's just network connections, what we talk about between these systems, and yeah, that's it, what we need. Then we have now this shop floor to top floor integration, what we have done. Now, I think everybody got the picture that we can have redundant or no redundant approach to one of the systems. One can be Windows, one can be Linux, it doesn't really matter. One can be version 3.20, one can be version 3.18, 3.19, it doesn't matter. It will communicate. Even a 3.1 version will communicate to 3.20, and that is 20 years of technology in between of them. So they can all be connected together with TCP, of course, in your network. We feature redundant network connection. I didn't mention, but it was on the slide for the redundancy, right? And we natively support redundant network connection. What is very important, you don't need teaming adapter or special hardware or anything, because all our managers natively support that. And then, of course, you want to connect the wide variety of user interfaces. And that might be our full client, the Qt-based user interface, what is available on Windows, Linux, Android, iOS. And yes, because Android and iOS, that is, of course, an app what you download from the store, and you can use it on your mobile phones. You can use it on your tablets. I know there are also Windows tablets or ruggedized tablets, what you use on the shop floor directly. Sure, that are all solutions what you can do with WinCC OA. If you don't want to install anything on a client machine, you can also use our ultralight client that runs in the web browser. So what is the thing you need to do is, on your main system, you start the web server. That is a control manager, actually. This is just one thing what you start, and that's it. It serves the data then to the user interface client of your choice. And that might be the ULC UX running in the browser, or a dashboard, what we mentioned earlier for the ProveIt solution. The dashboard would be an HTML thingy where you, the operator, is modifying the dashboard at will, at any time, and they produce their own views during runtime. But of course, engineering during runtime is also possible, and somebody can do that. And in the moment you do a change or you press the save button, it would then also be available for the other user interfaces and would be distributed, the new panels, the refreshed files, through the web server automatically. So that's the complete picture of how these architectures will work. But we have not yet talked about the integration with historical data. Where does the historical data occur? And that is, of course, on the shop floor somewhere in your different locations, maybe because of the small systems what you have distributed all over the world. There you will have some data gathering, you will have it on some other places and so on. But then you have your head system in the control room that needs this data. And always, if you would want to see some trends and so on, you would connect or collect this data via the maybe slow network connection, because that can be a WAN network connection to a completely different place. That would considerably slow down the communication. And this is why our next generation archiver with the plugin concept features, of course, an unlimited number of plugins what you can use in parallel. That means you can have local storage, maybe only for a short period in time, like 30 days or something like this retention policy. And then in parallel, you write to a central data server, your central data lake, what you create, because on the central server from multiple of the systems, you integrate everything in one common Postgre database, for example. And then, of course, the systems in the on your main control center, the user interfaces would directly get the data from your central data lake and not go via the network connection to the detailed individual systems. But if you start the user interface there, of course, it uses the local data. So that is the idea of having a completely flexible historical storage for all the data what you need. And then, of course, also we should mention this, that when we now want to serve all of this data, what we have now at hand on our data lake and in our head system, because we can address all this data from the other system on the fly, we of course, all our servers, what I mentioned earlier, the MQTT publisher, the OPC UA, they will be able to serve all of that from the head system. So you don't need to run an MQTT or OPC UA server at each of the small ones. No, only one time at the head system, of course, and that serves all of the data. So just that we also have this picture then as a final statement here. And that, of course, brings us to this UNS, the unified namespace, what we provide with then the head system to the outside world, where we then exchange the data with whatever thing you want to then connect to this UNS. And well, yeah, that have been the architectures. Now, to quickly summarize the key features or benefits of WinCC Open Architecture: platform neutrality, Windows, Linux, we run on AWS or Azure. On virtualization platforms, we're certified on VMware, but also Proxmox. And of course, we run on Docker environments, Kubernetes, and so on. The pure event-based communication is key for scalability, and of course for highest performance. The online engineering makes sure that whatever you do is immediately live. Every single thing you do is always with the running system. There is no such thing like compile or that you need to stop or restart the application or something like this. You create the tag, it's there. Yeah? You change some configuration, it happens. That's the point why it is called online engineering system. And then disaster recovery for the mission critical things. Fully integrated video system. Maybe we should also mention that that is an option. There is a video system from Excellence, what is directly integrated also without special hardware, just service driven, and with PTZ control of the live feeds, cameras, and all of these features, what you can dream of for a total video system, complete package, GDPR safe, and all of these kind of things, all encrypted and so on. Smart SCADA for the predictive maintenance decision support. I did already mention that. Coming with an R interface, we are using R as an interface to calculate all these things, what are needed for the smart SCADA analytics. And then, of course, reporting we do with SOAP interface or with Microsoft Excel, or, of course, the REST interfaces to connect to Power BI and using the data maybe there. Node-RED is also available as a connector. TIO portal, we can also get the engineering data from TIO portal and then create data point types and instances right with this data from TIO portal. And every of your application, what you do can be fully brand labeled. That means also for OEM customers, it is very suitable to do their own solutions and then sell it under different name. Scheduler, recipes, maps integration, OpenStreetMap or things like this, that is of course also there. ComCenter is sending alarms via cell phone, but you also have seen the Telegram application, what I explained earlier. But this can also be Microsoft Teams or any other connector to show the alarms in this application. And the advanced playback manager would be the action replay of a plant, where you want to then analyze certain situations on a separate system, on a copy of your original system, where you just play back an existing situation from the past, using for training, analysis, or this for your plant people. Yeah, creating your own drivers, I did already mention. And this is why actually all of the things you did see at the ProveIt was able to happen, and why WinCC OA is capable of doing that tremendous scalability and flexibility. Final statements here: security. All of this will be forfeit, of course, when you are hacked and when your application is brought down by some external bad boys. And this is why our system, no matter if we start with a small standalone system, all outgoing connections are, of course, encrypted. We can use different methods here. For the drivers, the connection to the field equipment, to the PLCs, we have the different driver protocols that feature encryption, like, for example, the 61850 or the S7 Plus, and many more, OpenCC OA. And then, of course, everything is with Open SSL, with TLS encryption to the higher standards, and of course also every other off-host communication to the user interfaces and everything what you connect from off-host. When we have a distributed system, of course that is the same case here, and of course also between the redundant systems the communication would be encrypted if needed. That depends on your security concept, what you do for your plant, where you need encryption and where not, but you can have all communication encrypted. And then when you have a mixed setup with different operating systems, different versions, different everything, of course, every connection can be encrypted here, and ensure, of course, when we have the need for presenting information to the outside world, we would maybe then establish a DM set where we place a web server and our multiplexing proxy for easy access from the outside world, without exposing your main servers in the DM set, but only the web server and the proxy, what is a port concentrator actually, and make sure that everything is encrypted. So that is the idea of encryption with the communication between the systems. And when we now check out what security or key security features are included in the system right away, first of all, we should mention that we are certified, of course, against the IEC 62443. And we fulfill 100% of the SL2 certification level. Yeah, maybe 95 for the SL3 and 92 for the SL4. And that is the highest security level in this guideline. So certification to a very high standard. All of that works with OpenSSL certificate, but also, of course, Kerberos. Kerberos is, of course, the go-to solution when you have a domain, like a Windows domain with domain server. The Windows servers come with Kerberos, and all our managers speak Kerberos natively. So that is the most easy thing to have the Active Directory synchronized in WinCC OA and use Kerberos for the highest security standard. For the drivers, BugNet Secure is available. IEC 61850, DNP3 does support security. The S7 Plus driver, of course, supports security. The OPC UA is supporting security. And yeah, maybe some more. There is a detailed security guideline available. It's a book of 368 pages. And this, of course, will be explained to you by some security trainings, what we also offer, of course, or also, of course, you can ask us for help. Our consultancies are, of course, eager to support you then in your security needs later on. There is actually where we finish with our presentation of what WinCC OA can do. That was the topics in a nutshell. I have to admit, we were going through the topics rather fast. Now you have done a lot of questions. I had always an eye on the list of questions coming in at the side, so we will have a short look there. Only one little thing what we are going to do first is, of course, I also want to a little bit at least show you what the system looks like. And we have the very short demonstration of one new thing that comes up, the module type package, MTP. Module type package is a thing what, of course, now is coming up for the different vendors when they provide applications, ready-made machinery with all of the engineering already prepared by them. In this package file, there is not only all this description of the machine, of the data model, but also the configuration, of course, of it, and then, of course, also graphical parts. So that is the proof of concept, what we just recently did. And let me share how that works. I just want to share my other screen. Was the screen share working, Leo?
Not yet, Marcus.
It was not? Damn it.
Yeah, maybe you can reshare one more time.
Screen to share. Why is it? So now you should see my other screen, right?
Yeah, put it in the full screen.
And what you see now, what you see now is the console where we have a normal project what contains some managers, what we have already learned beforehand. There is the event manager, there is the database manager, some archiving solution, there is some OPC client server, and then some manager that does some other magic. And we have the GEDI, what is the graphical editor. I'll start this project, and we also see how slow WinCC OA actually starting a project. And that is typically happening in under 10 seconds. Here we go. And the graphical editor would be the main development environment, what we not need in this proof of concept. And I also tell you why. The only thing what we need, sorry for that, is the MTP importer, because everything, actually really everything, will happen automatically. How so? The package what our machine vendor provided contains already everything. The package contains the content of the tags from the machine, but not only that, but also the configuration, of course, because it was engineered maybe with GeoPortal or other means. Also, it is an information about which driver to use. In this case, it is the OPC UA, what we are using here. And also, it will have some information about the graphics. The graphical library, what is used here, there is a guideline, IEC guideline about what are the standardized objects which are used or can be used for MTP. It's the CFL library, what we are trying here. Some of the objects for this proof of concept we did not implement all, and it's not yet part of the system. This I have to mention, but we can now see how that is read. It's a package, and what will happen next. First of all, I want to show you that The different types, ANA mon, ANA few, bin, mon, and so on, all of these standardized things which are there, mon, ANA drive, for example, and all of these, they are empty at the moment. No instances there. And only when we now would use our external tool, what actually comes with TIA Portal, and of course also WinCC Unified is supported, and that is also of course a main go-to platform for MTP at the moment. When we then have this file made present to this external tool, we can parse that package, and we will see that there is some metadata inside, that there is also some tags inside. This is of these different types, what I showed you before. And then, of course, there is also an HMI part inside. There is only one panel where there is, of course, the information, which object is on which place, actually. And that is what will happen. We will integrate now this thing. And wait a bit. Where is the instances? No, sorry, not this one. Here, instances, we add a new instance of that. Of course, we can have now multiple machines of the same type. This machine vendor sent us now 10 machines. Okay, we do multiple, but we have this definition file for that type of machinery. We give whatever name, and then we integrate it in the system. What you see in the background is that something here was already populated automatically, and also here some panels were produced. And why that? Because we created from all of this information from this package, we did create the data points. They come with a predefined structure. It comes with an address. Everything is predefined already. That is read from this file and created and up and running. And as I said, online engineering system means it is already up and running. And when we now go to the user interface part, also the panel was automatically created. And when we log into our system, we will now find that we have not only all the data, what is already connected to the OPC server of that machine and so on, but also here our process panel that was automatically created because of this information, what we did see in this little tool earlier. We did see the HMI part, which thing is on which position, and that was, of course, placed here automatically. Of course, you can do now some adjustments. Maybe if you don't find this nice, what the vendor supplied you with, then you would do some fine-tuning, but here we go. Okay, that's it.